Okay, so good evening, everyone. It is my pleasure to welcome John Barrett to give the 8th lecture in the OSMU 23 series. John is presently Professor of Mathematical Physics at the University of Nottingham, where he leads the research group on mathematical physics. John obtained his PhD from Imperial College London under the supervision of Tom Kibble, and subsequently held positions at the University of Zurich, Newcastle upon Tyne, Cambridge, and Penn State before taking up his current position in Nottingham. John has very wide-ranging research interest in gravitational physics. In particular, he has focused on quantum gravity and associated mathematical themes from quantum topology. He has also branched out into other topics related to gravity, most notably the non-commutative geometry of the standard model of particle physics. Among John's best-known works is the joint research with Louis Crane on relativistic spin networks in quantum gravity, also known as the Barrett-Crane model. I now welcome John to tell us about non-commutative geometry and its connection with the standard model of particle physics. Over to you, John.
Okay, thank you very much for that introduction. It's a pleasure to be here and to talk about the non-commutative geometry of the standard model. It's a subject I've had an interest in for a very long time. In fact, I was lucky enough to go to Alan Cohn's lectures about the standard model in about 1994, I think it was, at the Newton Institute in Cambridge. And he was just developing the real structure of the standard model, which I'll talk about. And he's a mathematician, but he's got a very deep interest in physics and developed this theory of non-commutative geometry in order to understand physical models better. And some of the motivating examples were things like the non-commutative torus, but also the internal space of the standard model was a big motivating example for the whole theory. It also has some roots in mathematics, in operator algebras, index theory, and so on. And so it's sort of a melding of the two things, but very much driven by interest in physical examples. So I got to play my own little tiny part in this in about the mid-2000s, when we managed to correct the internal space of the standard model. And more or less what I'm going to explain today is the outcome of that and where the theory was in about 2006, or perhaps a little bit later. And it reached a sort of a canonical form at that point. And since then, there have been various developments going off in various different directions about how to tweak the theory, add things, subtract things, unify things, and so on. And I don't think there's any particular consensus about what has happened since then. So I'm going to settle for describing, the way things were at the end of the 2000s, in a way, because that's something that everybody sort of agrees on, that that's where we got to. And so there isn't very much new in this talk. It's really sort of trying to explain what the basic theory is. And it's of particular interest to this audience, I hope, because it's very algebraic. And I've been sitting here listening to lectures about the algebraic structure of the standard model, particularly to do with octonions is the main title of the series, but other related structures like Clifford algebras and so on. And here in this non-commutative geometry, it's very algebraic too, but in a very particular way. And so I want to explain that as a way of contributing to exploring what the geometry and the algebraic structure of the standard model is. And I'm not going to mention the octonions, apart from just now, but I would dearly love to understand how the octonions fit into this picture. And perhaps, it's one of the things I'd like to think about. Yes, so let me get into explaining the detail, and perhaps there might be some discussion and questions towards the end. Yes, right, so I've said everything on that slide. And I'll attempt to change the slide to the next one.
You have the, oh yes, okay.
Okay, so so the basic thing is a spectral triple developed by Alan Kohn, and it has three things in it. Curly A, an algebra or a star algebra, curly H, a Hilbert space, and curly D, an operator called the Dirac operator. So we think of this algebra as the algebra of functions on a space, at least if it's commutative, that's certainly true. And the Hilbert space H, we think of as the space of fermion fields on your space-time, whatever it is, manifold. And by fermion fields, I mean the first quantized things. So like the things that you would put in to solve the Dirac equation if they were functions. I don't mean the space of quantum. I don't mean the Hilbert space of quantum mechanics. I mean the ordinary fields on space-time thought of with an inner product. And these fields have an action of the algebra, and which I'll just write as sort of left action here. L of A is my action. And the Dirac operator is, well, it's the Dirac operator acting on the fermion fields. And then there's various axioms in this. You can express all the properties you want of these things in terms of each other in a sort of self-consistent way. And the overall aim of the game is to re-express the whole of geometry and physics, if you like, in terms of these as the primary elements, and express all the axioms in terms of those things, and not mention other things like, the manifold and space-time or spinors or anything. So, there are sets of axioms here, and these axioms developed over time. I mean, they're not just sort of a God-given or they're not a Kohn-given set of axioms. They were proposed originally in the 1980s and developed. There was a major development in the 1990s with a thing called a real spectral triple, which I'll come to talk about. And then it got corrected, as I say, somewhere in the 2000s to get the standard model to work. And since then, there have been various adjustments proposed. You can add axioms, you can modify them, you can perhaps delete some axioms and see what happens. But most of them have a very, very good reason for them, and it's very hard to change. You have to have a really good reason to change the axioms, and people propose that, but then of course you've got to work out what happens when you do that. Okay, so I'll mention some of them as we go. I won't give a whole complete list now. But the big deal is that this algebra here can be non-commutative. And in the non-commutative case, it's no longer true that a non-commutative algebra is an algebra of functions on space. So this is very much in quotes here. It's very much just a metaphor and not an exact thing anymore. Okay, so non-commutative geometry is a generalization in which you hope that all the relations work in the same way, except that you're allowed to also have the algebra be non-commutative. And the fun thing is that this structure is already in physics, in the standard model, it's already there. Okay, so one extra little tweak to mention is there's also a gadget called the chirality operator. And this is fairly straightforward. It's an operator on the Hilbert space, which you think of as the fermion fields. It squares to 1 and it's self-adjoint. So that means its eigenvalues are plus or minus 1. So the plus 1 eigenvalues are the left-handed fermions and the minus 1 are the right-handed fermions. Okay. And then we have a fairly crude classification of spectral triples into even type and odd type. And the even type is where the Dirac operator anti-commutes with the chirality. In other words, it sends left-handed particles to left-handed fields to right-handed fields, and vice versa. And the odd type is where it commutes with chirality, so the chirality doesn't change. And you should think of this classification into two types as like the complex Clifford algebras, where there are exactly two types of complex Clifford algebras. In fact, they're also called odd and even, so it's a very close analogy. Okay, so The story on the previous slide is slightly modified, that there's also a chirality gadget, which wasn't big enough of a deal to make it called a spectral quadruple, because it's not quite as important as the other three characters, but it's part of the structure. Okay, so on to our sort of standard example from classical geometry. The space-time manifold, which is going to be called N, and to fix ideas, it's a 4-manifold, and I'm going to put a Euclidean metric on it, and it's a spin manifold. And the algebra A for the manifold, so this is a spectral triple that belongs to this manifold. So there's the little m's here are the subscripts. The algebra is the smooth functions on the manifold. The Hilbert space is the sections of the spinor bundle of the L2 sections, so it has an inner product and is complete and so on. And then you can act with the algebra functions on a spinor by just multiplying pointwise. So the left action of an algebra element on this spinor function at point x is you just multiply the value of function at x with the spinor field at x, and there you are. And the chirality is, as I said before, the left-handed spinors are eigenvalue +1 and the right-handed eigenvalue -1. The Dirac operator is the standard Dirac operator. Of course, you have the covariant derivative of spinors here. And then the coefficients here are the frame field, which encodes the metric of space-time. So the metric of space-time is, you can get, or the inverse metric you can get by multiplying two e's together and contracting with a Minkowski metric in the two indices A and A prime. And you get an inverse metric with indices mu and mu prime. So the data, if you like, of space-time metric goes into the Dirac operator. So it's a standard thing. And in fact, what Kohn discovered is you can invert this. That if you're given that somebody gives you the Dirac operator on a plate, you can then work out what the metric of space-time is. So if you like, the Dirac operator in this way is encoding the geometry. So we want to generalize this idea, and later on we're going to add to the Dirac operator gauge fields and the Higgs field and so on, and put all of the bosonic fields of the standard model into a sort of generalized Dirac operator. You can also discuss the Lorentzian case. It's a bit modified here. The sections of the spinor bundle you can still have, but they no longer have a positive definite inner product on them. So H in that case, in the Lorentzian case, is no longer a Hilbert space. It's a topological vector space with an indefinite inner product. So it's a bit more tricky, but you can modify this. And most of what I say will apply also in the Lorentzian case with suitable modifications. Okay, so now let's talk about the standard model. And here we have general scheme for it is the space-time manifold, which, as we've seen here, is a commutative spectral triple. And there's an internal space, which I'm going to call F. It's sort of called F for finite, actually, because you'll see it's going to be finite. And that will be non-commutative. And the non-commutativity is essential here, because that's actually what leads to non-commutative gauge groups. So what we do for the standard model is talk about geometry, the non-commutative geometry of the product space, M and F. And this is very much like the Kaluza-Klein idea. Here's sort of a picture of, this is the way I think of Kaluza-Klein. So the space-time manifold is like the top of your table, and then at every point on it, there's a little internal space which sort of goes off in the other direction. And all the fields at the point all run around that little internal space. So originally, the Kaluza-Klein idea, that was a circle, but it got generalized into other manifolds, and it's popular in supergravity and so on. But here, the big deal is that this internal space is a non-commutative space, and that's the origin of much of the structure of the standard model. And I have to say, this is a much better idea than the idea of having a commutative internal space in the Kaluza-Klein. It's just so much better that it wipes the floor with it. So anyway, on to describing it. I'm going to spend some time now describing the internal space of the standard model in this non-commutative geometry framework. So that will take quite a few slides. And then we'll come back to this product in a little while. So I'm going to talk about the standard model. And when I say standard model, I mean with a right-handed neutrino. That's sort of, for me, that's included in the standard model. And it would actually be awkward to remove it. I suppose you couldn't really remove it. So it's kind of got to be there, really. I guess you could give it infinite mass and then it wouldn't interfere with anything. Okay, so what's the algebra? So the algebra is, it's an algebra over the real numbers. And it's direct sum of three pieces. So the complex numbers thought of as a real algebra, two-dimensional real algebra. The quaternions and the 3x3 complex matrices also thought of as a real algebra. So that's the algebra for the finite space. Here's my notation for it. C is a complex number, Q is a quaternion, and M is a matrix. So that's a typical element of this space. And this is probably the most arbitrary feature of the whole thing, is this choice of algebra here. But, you know, and it's obviously a lot to do with the structure of the standard model. You can see right away how you could fit SU2 in here and SU3 in here. And we'll see that specifying this is more or less all you've got to do. Well, there's a little bit more, but not much more, to get the standard model to come out. Okay, so now we organize the fermions in the standard model into a 4x4 matrix. So this is one generation of fermions. So I've got the leptons down here, and I'm separating out the left-handed and the right-handed particles. So this is simply a 4x4 matrix, and it's got 16 complex numbers in it, and I'm just giving them names. I'm naming them as by giving them names of the particles in the standard model. So left-handed neutrino, left-handed electron, right-handed neutrino, right-handed electron, and then the left-handed up and down quarks, the right-handed up and down quarks, and they come in three colors. 1, 2, and 3. So altogether 16. And those are the physically relevant namings of matrix entries in 4x4 matrices with complex entries. And this is not quite the Hilbert space of the standard of a spectral triple yet. It's just a Hilbert space, and we'll make the spectral triple out of it in a few slides' time. But for the moment, just, you know, it's a stepping stone on the way. So I'm going to call it the smaller Hilbert space. So it gets a small curly h here, is its notation. So one generation of fermions here. Okay, so what do we do with this algebra? I'm supposed to act on Hilbert spaces with the algebra. So here we go. So I'm going to call pi1 of a 4x4 matrix. So I put the quaternion up in the little 2x2 block here. And then in this 2x2 block, I put a diagonal matrix with complex number C here and then C star, complex conjugate in here. And then this acts by matrix multiplication on these fermions on the left here. And I've just done this for you. So this quaternion here will act on the first two rows of this matrix here, and will act therefore on these doublets here, just doing the matrix multiplication. And this complex number C will act on the third row, and then the C star on the fourth row. So that's the left action of the algebra. So that's not enough yet to get the standard model. I mean, so, you know, we haven't even mentioned the 3x3 matrices, and so so there's more to describe, and the more is on the next slide. So there's also a right action of this algebra on this small Hilbert space. And what I do here is I put the 3x3 matrix down in a block here, and the complex number again in this first space here. And these little dots here are zeros. So in matrix notation, a little dot is a very small zero. My ease of writing. So now when I multiply on the right here, this matrix, with psi here is still this block of fermion names here. When I act on the right and do the matrix multiplication, this complex number acts on all the leptons down here, and then this 3x3 matrix acts on the right on the quark species. And obviously it's vector, row vector, multiply matrix, so it's acting as the color charge should do, at least if you had a group element in it. I mean, so I must emphasize there's a difference between algebras and groups. I mean, if you have an algebra, you can find group elements sitting inside it. But algebras are more primitive things, much more primitive. And that's part of the message. One of the messages I want to get over today, that the algebra action is a much more primitive thing than Lie groups. So what we see is that this small Hilbert space with these fermion species in it is a bimodule over the algebra. So a bimodule is a mathematical thing, and it just simply means you have the algebra acting twice, once as a left action and once as a right action, and the two commute with each other. And you can see that they commute with each other because they act with matrices. This one here on the left multiplied with the matrix on the left, and this one, the other one, I act with the matrix on the right. And obviously, whichever order you do them in doesn't matter. So that's the key requirement of a bimodule. So it's just a fancy way of saying I have two actions and they commute. So now, with that structure, I can identify what the gauge group is. So this is a derived thing. It's not, gauge group isn't fundamental in this whole game. So what's the gauge group? Well, it's the unitary elements of the algebra, which have determinant 1. So let's talk about that first. So firstly, it makes sense to talk about unitary. It's a star algebra. It has a star, which in any representation is just Hermitian conjugate. So whenever you act on a Hilbert space, it's just Hermitian conjugation. So U star is U inverse. That says it's unitary. And this pi2 representation, I should have determinant as 1. And in fact, you might ask, well, what about pi1? So let's go back to pi1. Well, actually, this determinant is 1 already, because a quaternion always has determinant 1, and the determinant of this matrix is C times C star, which is going to be 1 if C is unitary. In other words, it's a e to the I theta. It would be e to the I theta and e to the minus I theta is 1. So, whoops, no, I've managed to go right to the end of the talk. Help. So, where was I? No, yeah, right action. Yeah, the bimodule. Yes. Okay, good. So that's the unitaries. Yeah, and the determinant is 1. So for pi2, it's a non-trivial condition here, because this. So the determinant is what? It's C times det of n, which doesn't have to be 1 in general. So the condition is that is 1. So that restricts this group here to the gauge group. And this is called the unimodular condition. Determinant 1 is sort of unimodular. And it has a fascinating quantum field theory description in terms of anomalies, that if you don't have this condition, your quantum field theory ends up with chiral anomalies, which when you gauge them is fatal for the theory. So this condition does have a very good quantum field theory explanation for it. And it's a rather natural condition here, although it'd be nice to explain it better, perhaps in the future. Okay, so that's the gauge group. So let's explain it a bit more. I'm going to write my algebra element, my unitary algebra element, as before, as a complex number, a quaternion, and a 3x3 matrix. I'm going to split the 3x3 matrix up into a into a U1 element, a phase here, and this at the end here should say S in SU3, not M is in SU3. So the matrix here is determinant 1. So when you do that, the condition that the det of pi 2 is 1, so let's just flip back to pi 2, that is C times det of M, and det of M has now got t cubed in it, so that will be C t cubed is 1. Yeah, so C t cubed is 1 is the condition. So I can solve that for either C or T, and it's conventional in physics to write T as C to the minus 1/3, although a mathematician would probably prefer to get rid of C and write it in terms of T. It has a consequence that in physics you describe the charges as fractions of 1, which is sort of a little bit awkward, but you could just cube them all and describe everything in terms of T instead of C if you wanted to. But anyway, I'm going to follow this sort of physics convention and get rid of T by writing it C to the minus 1/3. So that solves this condition here. And then I can map my gauge group into U1 cross SU2 cross SU3. It's got the complex number, which is unitary, therefore it's in U1. It's the quaternion, which is also unitary, and therefore it's in SU2. And this combination, which is in SU3, because no, that should just say S. There's another typo in this, so that C shouldn't be there. This should just say S. That's in SU3. Okay. Right. And then you can go about calculating the what's called the adjoint action. So if I have an element of the gauge group now, this adjoint action, row view, you do pi 1, my left action on the left of the matrix, and simultaneously the right action of U inverse on the right. And when you do that, you then get the familiar table of charges of particles in the standard model. So how does this work? Let's just have a look. So for example, if I have a doublet here, the left and neutrino and the left electron, then the U1 charge is C inverse, and it's charged under SU2 in the fundamental of SU2. And you can see that from the previous thing. So where does that come from? It comes from, I guess, from pi 1. This is where the charge Q comes from, and then so that's acting on here. But then the other piece comes from the action of pi 2. It's this C here acting separately on the two components of this doublet here. And because of the adjoint action having an inverse here, that then turns into C inverse. So that tells you that the hypercharge of this thing here is -1, and it has SU2 charge and no color charge. So I hope that's possible to follow. Let's just look again at the left-handed quarks. So here the quaternion story is the same, so it's still got a SU2 force. But now the difference is that what happens on the right here is the multiplication of S, not multiplication of T. Sorry, not multiplication of C. So this is the pi 2 thing. I'm now down in using this block here. So I'm looking at these things here with the multiplication of M instead. So so then I get, yeah, so then I get the SU3 charge here, and I get a U1 of T inverse, which comes from somewhere. Where does that come from? Just blanking here a minute. Comes from using myself here. Yeah, the combination of M here, which has got right. Oh, yes, from M has got a T inverse in it. So sorry, no, M has got a T in it. That's right, and T is C to the minus a third. That's right. So then you see here, and then there's the inverse there, turning it into C to the plus third. Right. So you get the hypercharge of the quarks is 1/3. And I'm not going to do the rest, but you can go through the rest and check that all the charges come out right. So the upshot of this is that the standard model charges are determined by the action of a bimodule over an algebra. And this is very, very, I mean, I have to emphasize, this is very, very surprising. I mean, algebras have very few representations, very, very few. So, so let's go back to the algebra we've got here. What about the quaternions? Well, that's only got one representation, one irreducible representation, and that's its fundamental. That's it. And the complex numbers here have only got two representations. You can represent it as a complex number or its complex conjugate. That's it. And the same with the 3x3 matrices. You can represent them as the fundamental or the complex conjugate. And then when you have a direct sum of these three things, the only options you've got is to represent one of them, one of the things, and forget the other two. So that's why this pi1 here, you can pick here the quaternion, you can have C or C star. And in pi2, you can have C or M. So you can mix this up a bit. You could have some C stars or some M stars, meaning the complex conjugate, not the Hermitian conjugate. That's it. So you can play around with these things, but there's not much. There aren't many choices you can make here, and in particular, there's not even a fundamental representation. You can't send an algebra element to the identity or something. That doesn't make any sense. And you can't tensor product them. So you can't almost all of Yang-Mills systems you might sort of dream up and try and write down are not allowed in this non-commutative geometry game where an algebra is fundamental. There's a vast zoo of possible Yang-Mills Higgs systems. I haven't got onto the Higgs yet, but same is true. There's a vast zoo of Yang-Mills Higgs systems which you just can't write in this way. So the fact that the standard model comes in this form is very, very surprising. And when you first meet the standard model, you get used to the fact that there are three possible charges. There's a U1 charge, SU2 charge, and an SU3 charge. And some of the particles have all three. So you might think, well, how does that end up as a bimodule? Scratch your head. And the answer is this little fiddle with the unimodular condition means actually there are only two charges when you rearrange them in the right way. There's a left-handed charge and a right-handed charge, and that's it. So so there is it is very surprising, this this structure. Okay. Right, so now I want to come back to explaining how that fits in with what I said about spectral triples. And so there's a little bit more theory. This isn't quite the Hilbert space of the spectral triple yet, this small Hilbert space I described. So a little bit more to describe what a real spectral triple is. So a real spectral triple is sort of a very general notion of spectral triple. And the standard model is an example of it, but there's lots of other examples. So for example, if you take a commutative spectral triple, you can make a manifold in the sense of an ordinary spectral triple, A, H, and D. And typically what you get there is you get a spin C manifold. You can describe spin C manifolds. And there's even a reconstruction theorem which tells you that every spectral triple with blah, blah, blah conditions is a spin C manifold. But you don't get spin manifolds. You don't get down to spin C is more general than spin. It has an extra U1 in the spin grid. You have spin cross U1 in the spinor transition functions. And if you want to get yourself down to spin manifolds, you have to have a real structure. And it's a long story, and it's a lot to do with Clifford algebras. There's the difference between complex Clifford algebras and real Clifford algebras, the tenfold way that John Byers talked about, for example. So the real structure here is the real structure in that sense. Anyway, so let's describe it. So now our spectral triple has four things, a bit like the trilogy in four parts that Douglas Adams joked about. The algebra, Hilbert space, Dirac operator, and the real structure J, which is an antilinear operator on the Hilbert space. And it squares to epsilon, which is just plus or minus 1. And plus 1 is called a real type of real structure, and minus 1 is called quaternionic type of real structure, which is familiar yoga from Clifford algebras. And what this real structure is good for is that you can define a new action. In fact, you can define a right action of the algebra on your Hilbert space. So what you do is you take the left action of A star, and star, of course, reverses the order of operators, it's Hermitian conjugation. And then you sandwich with J and J inverse. So you do the antilinear thing, do this action, then J it back again. And that's a right action. It's linear in A because the star complex conjugations cancel by the antilinearity of the J gadget. And it's a right action of the algebra on your Hilbert space. And the big axiom of this whole deal is the left action and the right action should commute. So you can do LA and RB in either order. It doesn't matter. And so when you've got this, H is a bimodule over the algebra. So getting similar to the structure I just described for the standard model here. But it's a much more general framework. So how does the standard model fit into this? Well, getting ahead of myself here, there's an extra slide here about general stuff here, the eightfold way. So I was talking about how you see, in fact, 8 types of these real structures on spectral triples, because there's a number of signs you can have. So I already mentioned one, that the square of J is plus or minus 1. But J can commute or anti-commute with the Dirac operator. So that's another sign, epsilon prime, in this row of this table. And it can commute or anti-commute with the chirality operator, and that's the third sign, epsilon double prime. And these values, plus the specification of whether it's an odd or an even type, actually tell you which of the 8 types of spectral triple you've got. And it's very much like Clifford algebras. In fact, when you talk about commutative spectral triples as being manifolds, then it turns into a description of Clifford algebras, the Clifford action of vectors on the spinor bundle. So this is all very much tied up with, it's very similar to the eightfold way for Clifford algebras, spin bundles and manifolds. Yeah, okay, so that's general stuff out of the way. So how does the standard model internal space fit into this? Well, what we do is we take that little Hilbert space I had described before, and I direct sum with a copy of it, which I'm going to call the conjugate, little h. And here are the conjugate fields. They look like the original fields, but it's been flipped on its side by like a Hermitian conjugation. And so I've transposed the matrix I had before and put bars over all the things to give them different names. And these are the components of conjugate fields. So what we do is we make a Hilbert space where we have the fields and the conjugate fields all sitting together in the Hilbert space. And that is the Hilbert space of the spectral triple. Okay. And there's a very nice sort of matrixy way of describing this. You put my original 4x4 matrix in a top right block here. My conjugate fields go in the bottom left block here. And so it's sort of block off diagonal 8x8 matrix is where all the fields and their conjugate fields in the standard model live. So it's a 32-dimensional vector space. So I must emphasize these numbers here are all independent variables, independent of the original field here. Of course, there is a J operation, which is Hermitian conjugation of this matrix, which will send one into the other. So that's sort of charge conjugation, if you like. Okay. And then in the sense of the spectral triples, what's the left action? Well, what you do is you use pi1 and pi2, those two little 4x4 matrices for the action, in a diagonal configuration here to act by matrix multiplication on these fields and the conjugates. And then the right action is you use the same matrix but multiplying on the right. And then you can see that the left and the right action commute. Obviously, it's a bimodule. And actually, you can see that this J here does the right thing for the axiom here. It intertwines the left and the right actions. That's what this thing here says, that J intertwines left and right actions. So they're not independent. One is determined in terms of the other. And you can see that here, that the J operator, because it's Hermitian conjugation, it flips a matrix on its side. So obviously, left becomes right and right becomes left, and that's the little calculations do. You can see that LA turns into RA when you do that. Okay, so that's how the standard model turns into a real spectral triple. Okay, so you have here now the Hilbert space. And I should have written HF here, so it's the Hilbert space for the finite space F. And that's the action of the algebra. Yeah. So yeah, it's got its little HF on here. I described one generation, that you can have 3 generations if you like. You just tensor by C3 or write it as 3 copies of H1, and you get 3 generations. This theory doesn't have anything to say about the number of generations. Unfortunately, it'd be nice if it did. You can have as many as you like, and it doesn't seem to be a constraint. But when you make a Hilbert space with more than one generation, there's more room in the theory to put in mass matrices and so on, and they come in very naturally. So it's not wasted, this formalism. Okay, so this Hilbert space HF has dimension of 96, and so that's these matrices here. This is 4x4, so that's 16, that's 16, that's 32 for one generation, and then 3 of them, it makes 96. Okay, so that's 2 bits of the Hilbert space for the standard model. That's the algebra and the Hilbert space. So 2 bits for the spectral triple. And now the 3rd bit is the Dirac operator. And this is where it gets interesting. And a lot of because now we're not just talking about algebra and gauge groups, we're now talking about the dynamics and how the fields interact with each other. And that's coded into this structure of the spectral triple as well. So plunge into the axioms for the Dirac operator. There's 4 main axioms. Firstly, it's the self-adjoint operator. Okay, fine. Then it commutes with the real structure, which I already had in that table, and I'm talking about the even case here. So this is all +1, not -1. And again, in the even case, anti-commute of chirality. Okay, so that's fair enough. And here's the big extra axiom. It's called the first order condition. And it says if you take the commutator with the left action, and then you take the results and take the commutator with the right action, you get 0. And this is for all A and B in the algebra. And it's a very clever generalization of the condition. If you write the Dirac operator on a manifold, and so let's just sort of go back to that for a minute. So I had, where did I have it? This operator here. You could ask, well, in the manifold case, what makes this formula like this? So abstractly, if I just write down some operators and some axioms, how does it turn into this? And the answer is, well, this is a first order differential operator. And how do I make sure it's a first order differential operator? Well, the answer is, if you commute with functions here, this algebra is an algebra of functions. If I commute, take the commutator of D with a algebra element, and if it's a first order operator, the commutator will be a zeroth order operator. Takes the order of derivatives down one. And in fact, what is it? Well, it would just be the Clifford multiplication of the gradient of the function that I put in. I take the commutator. And then that thing, because it's a zeroth order operator, will commute with any other algebra element. So in the commutative case, the left and the right actions are equal, same thing. And you would just have this equation here. Go back to it. In the commutative case, you'd have this equation where L and R are equal. You just have the commutator with the left action, and again with another left action is 0. And that would tell you that Dirac is a first order differential operator. So in the non-commutative case, this is the right generalization of that formula. And we can apply this formula to the standard model internal space and ask, well, what do you see when you solve this equation? And it's very constraining. I mean, remember the Hilbert space of the internal space of the standard model is 96-dimensional space. So in principle, D is a 96 by 96 matrix. Okay, it's a bit smaller than that because it's got to turn the left-handed particles into right-handed particles. Okay, so that cuts you down by half. But there'll be a huge amount of space in that operator. But these extra axioms here then cut it down a bit more. But this first order condition cuts it down hugely, and the amount of data left is actually very small. So in this case where the Hilbert space is finite dimensional, as we have for the internal space, where it's this 96-dimensional space, we can write a formula for the general Dirac operator that satisfies all of these conditions. And the thing that makes this easy, which you can see from this, is that all of these conditions are linear in D. Only one D in all of these equations. And so it's just a load of linear equations for D. So of course you can solve. And with a bit of thought, you can work out formulas and then nice formulas for whatever's left in D. I'll just mention here, just so to mention that life isn't always easy. If in the infinite dimensional case, you can't just do this straight away because you need more axioms. So for example, if you're describing a manifold, which has a Hilbert space of spinors, is certainly an infinite dimensional Hilbert space, sections of a spinor bundle. Of course, the Dirac operator is now an unbounded operator, whereas the algebra curly A is an algebra of bounded operators. And then there's some, lots of stuff to say about, unbounded operators. Tricky. They have a domain of definition, and what happens when you take the commutator of the Dirac with algebra element, is that bounded or unbounded? You've got to have an axiom about that, and so on. And so working out the axioms for the infinite dimensional case is much more complicated. But it is possible to do that. And Alan Kohn has a manifold reconstruction theorem, which actually took quite some years to work out. But there's a way of adding axioms so that it's the only spectral triples you get in this commutative case are manifolds. But anyway, so I'm not terribly interested in that. In the finite dimensional case, everything is easy. You don't have to worry about the domain of definition and operator. They're all defined on everything. And so all you have left is these linear ones, and life is easy. Okay, so I'm going to skip over the mathematics of how you solve these equations and just describe to you what the result is. So this is what the internal space Dirac looks like. DF is what it's called. And what is it? It's the sum of two pieces, which I'm going to call D right and D left. And D right is actually things that commute with the right action, the algebra. And D left is things that commute with the left action. And these two pieces are not independent. In fact, D left is just flipped by the real structure from D right. And obviously J flips right action to left action, so that's not surprising. If you apply J, if you sandwich J and J inverse around this whole equation here, it'll tell you D left commutes with the left action. Okay, so we only have to describe D right. And here it is, D right on a element of the internal space, Hilbert space, is a sum of terms that look like this. There's a matrix M acting on the left and a matrix P acting on the right. P has to commute with the right action, and M is any matrix as long as it anticommutes with the chirality. And you can fiddle around with these constraints and work out what they are. And I've just done one of them for you, one of the possible terms in this sum here. P is a matrix which is the unit matrix on a 3x3 block. Remember, these are 8x8 matrices. And that 3x3 block shall pick out the quarks here. The quarks in the fields in the block psi and not in the conjugate fields. So that's what this 3x3 block picks out. And so when I multiply by P on the right, I just get these two things, and everything else turns into zeros. And then on the left, I have the matrix M here, which is sort of block off diagonal. These are two. I feel like I've missed something out here. Yeah, there should be two copies of this in the matrix M. But anyway, the upshot is that N and N star have to act on. Yeah, I've missed out. This is a 4x4. N is 2x2. This is 4x4, and there's another block here to make it up to 8x8, which is all full of zeros. Yeah, but the upshot is here of the multiplication is that N and N star act on these quarks on the left here. So in particular, they mix the up and down with the same color. So this is sort of it's interacting with the weak charge, if you like, of the quarks, but not the strong charge. So that's one term in this sum here, and there's other similar terms for other choices of P. What this gives you is it gives you a mass terms for the quarks. So if you have a Dirac operator here, so what these matrices do is it's interchanged left and right because this is off diagonal, and it's multiplied by something here which will have masses in. As you know, if you diagonalize them, there'll be mass matrices, and these turns into the mass terms for the quarks. So the other terms in this sum here for the Dirac operator give you mass terms for leptons, also Majorana mass terms can also come into this Dirac. And what's in the N matrix? Well, right, interestingly, it's packaged up. You see, in the standard model, a mass term for the quarks will involve the Higgs field, because you can't just have a Dirac mass term because of the gauge invariance. So actually what you find is this matrix N here has an action of the gauge group on it. So some of these components here in these matrices turn out to be Higgs fields. And you can work out which very easily by just looking at the action of the gauge group on them. And the ones that are left, you can just set them equal to be constants. And they're typically the the constant terms. But also, if you want to, you can promote them to be scalar fields. So, for example, the Meyer and the mass terms are constants normally, but it's possible to have some of them to be scalar fields. The theory doesn't tell you which to do. There's some freedom here. Okay, so the Dirac operator is actually very interesting. It has a way of coding in both the Higgs fields and the remaining constants in the mass matrices. And exactly all the thick fields that you want and all the constants you want are allowed in this matrix. There's actually a few extra terms that are allowed, but you don't want. Not many, but a few, which you can set to 0 if you like. Okay, so that's the internal space described. And we finally get to the whole standard model. And remember, the idea is that you have a product here of the manifold and the internal space. And so that's achieved at the spectral triple level by tensoring the algebras, tensoring the Hilbert spaces. And the Dirac operator on a product space is the sum of two Diracs, sort of, if you like, the Dirac. So it's the product metric we're describing. There's some sort of metric geometry on space-time and some metric geometry on the internal space. And the product is the Dirac operator on space-time and the Dirac operator on the internal space. And you have to put in a chirality for one of them so that the two bits anti-commute in the right way. Okay, so that's called D0, and what it is, it's the vacuum geometry. It says if you have space-time in the internal space, it just tells you what a sort of vacuum configuration is. And particularly when we talk about vacuum, it means there's no gauge fields. The gauge fields have all been set to 0, because in this description, the gauge fields turn out to be off-diagonal terms. They don't sit nicely as a product of things. They are some of the terms that mix the manifold directions and the internal space directions. So, so the full Dirac for spectral triple for the standard model is this vacuum one, but plus some extra terms, which is where the gauge and the non-vacuum Higgs lie. So the fluctuations away from the vacuum Higgs configuration. So, for example, the Higgs particles, which can vary from point to point, are living in this omega here. Okay, so the vacuum Higgs field is a constant, same at every point in space-time, but when you allow it to fluctuate, it can vary in space-time. So there's a particular ways I'm glossing over here to describe what these allowed omegas are. So there's again some strict rules as to what you're allowed here, but that's where the gauge and the Higgs fields lie. So to give an example of this formalism, in this tensor product here, remember the finite Hilbert space just had names for the fields and the conjugates, but this manifold Hilbert space has the whole spinor field in. So, for example, a typical product element in here would be psi of x, so that's a spinor field on the manifold, and then the name of some field here, so that would be EL. So this thing here would be a spinor field for the left-handed electron. So whatever matrix component you put in there, it tells you that it's that particular field that you're talking about in the standard model fermion field. Okay, and here in this product space, of course, every fermion type will end up picking up a whole Dirac spinor on the manifold. And that's sort of wrong in the sense that if you have a left-handed electron, you only want it to have a left-handed spinor field associated with it. If it's right-handed, you only want it to be right-handed. So there's a constraint, sort of chirality constraint, which says that the two chiralities have to match up. So the manifold chirality and the internal space chirality have to be the same. So that's constraints written like this, that if I have formed the tensor product of the two, it has to act as the identity operator. And that gives me this sort of positive H, what I call H plus, or sort of the physical Hilbert space of things with the right chirality, where whether you either have that the manifold chirality is 1 and the internal space chirality is 1, or you have that they're both -1. So in other words, the chirality of the spinor field on space-time matches the chirality of the naming of the particle on the internal space. So that's the sort of chirality subspace here. And this whole chirality is very important for physics, obviously. Having a chiral field is a key thing, and it's very restrictive. For example, you can't just put the standard model on some other manifold in another dimension. That actually doesn't work because of this chirality restriction. So here is, in fact, the functional integral for fermions. So you take these fields in this positive chirality space here, and I take the Dirac action here, and e to the I this, and I do the fermion function integral over the fields and their conjugates, and you get some sort of Pfaffian here. And that's how you do the functional integral for fermions. And this only works in all the right dimensions and with the right definitions of all the chirality operators and so on. So that's, so all of this is all geared up to work with the chiral theory, and indeed it delivers a chiral theory. There's a slight thing I've glossed over here, which is that I've kind of written this formula for the Lorentzian theory with an e to the I stuff and so on, and the Lorentzian Dirac action. But actually the way most of the formalism goes is through the Euclidean theory, where the Euclidean formalism is related to this, but slightly different. So you have to work out the Euclidean version of all of this. And there's a similar formula here in which you really do get a Pfaffian effect. Okay. And it also answers this question. There might be questions about fermion doubling. So when you make this Hilbert space here with this small Hilbert space with all the fermion types, and then you add in the conjugate fields, it looks like you've sort of doubled up and you've got the fields and their conjugates in there as independent entities. And people go, oh, doesn't that mean you've got fermion doubling? And the answer is no, because in the functional integral formalism, when you integrate over a fermion field, because it's a complex field, you have to integrate over the fields and their conjugate fields as well. And when you do that, well, if you forget Majorana mass terms and just have Dirac mass terms, you can always have a sort of complex Hilbert space formalism where you forget the conjugate fields and just write the Dirac action with just the fields and not their conjugates. And then the resulting thing is a determinant of the Dirac operator on that smaller Hilbert space. And the Pfaffian I'm describing here, which you get because the fields have been extended to include the conjugate fields, is then the same thing, because the Pfaffian of a big thing is the Pfaffian as the square root of the determinant, but it turns out to be, it's also a determinant of the Pfaffian, how to say this, Pfaffian is a determinant of a smaller block in the matrix, in the antisymmetric matrix. So you can rewrite this Pfaffian in the case where there's no Majorana mass terms, just in terms of the determinants of D on the smaller Hilbert space. So that fact is sort of somewhat confusing, because in the standard model you have Majorana mass terms, and you can't do this trick. When you add the Majorana mass terms in, your Dirac operator isn't linear anymore on this smaller Hilbert space. So you really need this bigger one with the conjugate fields. And then the answer is you can't go to Fathian. Okay, so that's the formalism. And so that's the fermion action. The thing that's remaining is the boson action. So I'm going to briefly describe that. And then I'll be more or less done, just into the discussion phase. So since my original brief was to describe the spectral action, I feel I've got to mention the spectral action. So here it is. It's the action for the bosonic fields. And I'm assuming now I'm flipping into Euclidean quantum field theory to make life easier for myself, because here we then have Hilbert spaces. So the Euclidean action, the spectral action, says that all the action is it's the trace of some function of the Dirac operator squared. And I'm going to assume that the Dirac operator has a discrete spectrum, as it does, for example, on a compact manifold. In fact, that's even true on a Lorentzian compact manifold with boundary. So this is not too bad. And on that case, when the spectrum is discrete, of course, you can work out this trace, certainly in the Hilbert space theory, by just looking at the eigenvalues. So you just have the eigenvalues of the Dirac squared, which is lambda. Well, the eigenvalues of the Dirac lambda. So you have f of lambda squared summed over the eigenvalues of the Dirac with multiplicities, obviously. So this formula here, very simple formula for the action, was proposed by Conj and Shamsuddin in 1996, called the spectral action principle. And in their paper, they had a proposal for the function f, that it's some cutoff function of the Dirac operator divided by a constant called m naught squared. And the role of m naught squared is simply it's the cutoff scale. So it's just put in to allow. So basically, it's saying that the cutoff function f has a parameter. That's all I'm saying. And the parameter is a rather simple one. It's you make d dimensionless by dividing by some mass scale, and that the mass scale is that parameter. And their cutoff function is something that looks like this. It's more or less constant at low energies, and as you reach the cutoff scale, it goes smoothly down to 1. So it basically just remembers all the eigenvalues below the cutoff scale and counts them all, in fact, with weight 1, but smoothly cuts you off at some scale, which is unification scale or the Planck scale or something very large, very high energy scale. Okay, so that's the Conj Shamsuddin. You can play with chi if you like. You can have different shaped chi's. And the only criterion is you, of course, want this to converge. So chi can't be wild at infinity, but some sort of shape to make this convergent. If you like, so you can make your own spectral action principle if you like, and dial slightly different physical properties that way. Anyway, so let's carry on with the Conj Shamsuddin formula. And I've stolen all this out of their paper from the spectral action principle from 1996. And here is the asymptotic expansion of the spectral action. So you notice it's plus order 1 over m naught squared. So it's higher order terms. So it's this is very much like a heat kernel. You can turn this into a heat kernel expansion by doing some sort of Laplace transform. And you work out terms by looking in Gilkey's book and working out the heat kernel coefficients. And this is what you get. I'll vaguely talk you through the terms here. The first one is the integral of root g, so the volume of the manifold with some constants in front. So a cosmological term. The second term is here involving the scalar Einstein-Hilbert. It's the scalar curvature here, so the Einstein-Hilbert action, but also a term involving the square of h. H is the Higgs field in this notation, with some constant in front of it. So that will in fact be the mass term for the Higgs field. Then the F4 terms out of the heat kernel expansion give you various curvature squared terms, very specific ones. You're not allowed any curvature terms, but these specific ones. That's the Weil squared, and this is Ricci scalar and from the Ricci tensor. Then you're allowed terms with the kinetic term for the Higgs field here, both here and in fact here. This has got derivatives in it, so that's some more kinetic term for the Higgs field. There's a Higgs gravity coupling, which is actually very interesting. Cosmologists like this. So this is, does stuff to your early universe and the symmetry breaking and so on. Then you get Yang-Mills terms. These G squared, F squared, and B. These are the Yang-Mills for the U1, SU2, and SU3 gauge fields in some order. And then finally, this quartic term here in H is the Higgs quartic potential. So just for completeness, I mentioned what all the constants are. You've got here that this constant y squared is is quadratic in the mass matrices. These are the K's in the mass matrices. Z squared is quartic in the mass matrices and comes into the Higgs quartic term. Covariant D of H is, of course, the covariant derivative of the Higgs field that comes in, so it's got the couplings with the gauge fields correctly. Oh, and then the F's here, finally these constants here, F, they come from the shape of the cutoff function. So remember the chi thing. So there are various moments of its shape. F naught is a moment, and F2 is just the integral, and the other F's are F4 particularly is just the value of chi at 0. So you can play around with the shape of this quite a bit and dial these different constants. You can try and make the cosmological constant vanish if you like, and so on. All the signs come out right, which is good, and all the terms that you want are there. Also good. So you can also play games with induced gravity. You could actually think of this as somehow an induced standard model from some sort of fermion system, but it's another thing I'll not go into any detail about. Right, so that is the spectral action. So I've described this non-commutative geometry of the standard model. And so it just remains a brief discussion of what the gains and what the possible issues are with this theory. It understands a lot of the structure of the standard model. I mean, a lot of the things that are arbitrary about it are no longer arbitrary. They really do come out of this theory with very few axioms and assumptions. And most of the axioms are very general axioms that apply to a whole load of other mathematical things. And so, you don't really change them too much. And remarkably, a lot of the structure of even the interactions between the fields comes out of this model. The non-commutative geometry is highly constraining. The fermion and Higgs charges come out just by describing the fermions as forming a bimodule over an algebra. And it's a very simple construction. And I'll emphasize again, vast majority of all the possible modifications you might want to make are just not allowed. So it's a huge coincidence, if it is a coincidence, that the standard model happens to have this sort of description. Now, I don't think it is a coincidence. I think it's telling you there is non-commutative geometry. It predicts the right antineutrino should be there, because otherwise you'd have a 4x4 matrix with an entry missing, which would be weird. And it predicts that you have a seesaw mechanism. So a particular way of coupling in making mass terms with a Dirac mass term and a Majorana mass term in a particular way. And there are various other schemes for neutrino masses which you can't fit into this non-commutative geometry framework. So it's definitely predicting the whole structure of the neutrino sector. There are a few beyond standard model additions allowed. For example, you can have a B minus L U1 field, U1 field, gauge field that couples to the B minus L charge. That's completely allowed in this framework. And it's allowed physically. It's possible. It's not, physicists can't kill it off, so that's good. There's a scalar field you can smuggle into the formalism. So remember, when I looked at the allowed Dirac operators, you have, for the internal space, you have various matrices, various terms that I had allowed. And some of the terms, here we are, like this, turn out to be mass matrices. And some of them are constants. Well, you can promote some of those constants into scalar fields if you want. Formalism doesn't stop you. And one of them is very interesting. It's called the sigma field. And it stabilizes the Higgs mass. So the Higgs mass has a horrible problem with running. If it becomes unstable at some point. And so if you're just on its own, the standard model kind of doesn't work because at some not too distant high energy, the coefficients in the action go negative, and which is a disaster. The quartic term goes negative. I think that's the way it works. But if you add the sigma field in, that stabilizes it. So that's something that physicists are interested in independently of this non-commutative geometry, but it's allowed in the theory. So that's an interesting thing. And also it predicts its couplings to gravity, so you can do cosmology of it and so on. So the gravity couplings are highly constrained. You can't just throw in any gravity terms or any gravity couplings you like. They're predicted for you. Okay, so that's the gains. There's various issues which I've listed and kind of run out of papers on this slide, so I stopped listing issues. But a few unphysical fields are allowed in this way I've described it, this sort of 2006 version of non-commutative geometry of the standard model. They're allowed in the theory, they're not required, so you can just quietly set them to 0 and say they're not there. For example, you can have leptoquarks, which are bosonic fields that couple leptons and quarks, which you really shouldn't have. But there is a space for them in this theory. So you might ask, the second point is you might ask, could I constrain these? But are there more axioms to be found to constrain these sorts of things don't appear? And various other things could happen. For example, this theory would allow you to have a massive photon just by the Higgs being a different configuration. The Higgs, the electroweak gauge group U1 cross SU2 acts on the Higgs fields, and there's nothing to stop that orbit being of U1 cross SU2 being not having any stabilizer subgroup. And if there's no stabilizer subgroup, then there's no massless gauge fields left. So that's a possibility in this theory. So there is some mystery as to why the Higgs field is arranged so that the photon is massless. And again, you might want to add in some more axioms, so it always comes out that way. you might want to go in the other direction. You might want to sort of have a unification. You might, so one of the big questions is, well, why is the algebra, this funny thing that I said right at the beginning, this algebra here, can't I make this look nicer? And indeed you can. I mean, there are various ways of, and look nicer means make it bigger. And that's the sort of unification game, because if you have a bigger thing, for example, you might want to unify one of the C's somewhere in the M3 C's and make M4, make 4x4 matrices, and have SU4. And you could also make the quaternions bigger and have two of them and have two SU2s and so on, and have a Patti-Salam model. And it's possible to do that, but at some cost. To where I was. And you can do that, but in order to get there, you have to throw some axioms overboard. It's not compatible with the chirality operator. So, or you can even make the algebra super big and just have M4C and M2H. So Patti-Salam would sit in there with, if you break this M2H down to H plus H, then the unitary elements of that would be SU4 here and SU2 here, which is how the Patti-Salam arises. But to get this algebra even bigger, you have to throw away some more axioms. You have to throw away the first order condition on the Dirac operator. And that's a very serious change to make. So what your job now is to explain as to how these axioms that you like to give you the actual standard model, how they reappear at low energy. Why you can certainly write down a vacuum configuration at low energy that obeys these axioms, but why would physics choose that? And that's an unsolved problem. So at the moment we have a sort of mathematical unification whereby I can just arbitrarily, by changing it, say, well, yes, look, I can make some nice big groups, gauge groups, and with some nice big algebras that look very neat. But it leaves aside the physical question as to why did physics choose the standard model at low energy. But I think it's a very interesting question. It's something that should be done on. And then, and more questions is what fluctuations are allowed. I mean, I sort of skated over this a bit. It's actually quite a big topic, is the fluctuations here. You start with your Dirac operator, and there's some process with all this data you have, you can work out a scheme for working out what the omegas that are allowed are here. And if you get this right, this is your gauge fields. And well, the gauge, there's a minimum set that you must have, and that includes these gauge fields. But you can then make it bigger. You can allow some more fluctuations, and there aren't at the moment any rules on how much bigger you can make this. So you might say, well, I'm going to go the full whack and I'll put in everything allowed by all the axioms of spectral triples, and then that's a huge set of extra things. And I don't think anybody's actually seriously analysed that yet. So that'd be a very good question. Probably you'd find that most of the things would be sort of Planck mass or something, and therefore you'd never see them. And I like to think that the things in the standard model are just the low energy fluctuations, and there may actually be a whole load of high energy fluctuations that we never see because they're unification scale or Planck scale mass or something. So it's possible that there's another story to be uncovered as to what allowable fluctuations are. Then possibly all fluctuations allowed by the axioms could go in there. So that's still an open issue in my book. And it's bound up with, I've got to say, my own hobby horse is, should space-time itself allowed to be non-commutative, which is a big whole load, another big set of issues and fascinating question, because let's look back at this product space here. Isn't it weird that this finite space here should be non-commutative, and that seems to be the golden extra ingredient that makes everything work. It gives you non-commutative gauge groups and gives you all the interesting structure of the Dirac operator and Higgs fields and everything. Isn't it funny that that's non-commutative, but this algebra here is still stubbornly commutative? Why would the universe have a non-commutative structure to it when one part of it stubbornly remained commutative? That's, to me as a physicist, that's sort of weird. So, you know, my personal project is to make this thing non-commutative as well. And then actually the formalism simplifies, because everything is then on the same footing, but it becomes physically unfamiliar, and you have to, you know, start to understand what it means to have a non-commutative space-time. But typically what happens is that that when we start to do this and talk about non-commutative spacetimes, they typically look commutative at low energies, and the non-commutativity comes in as you go higher up the energy scale. So it's not sort of incompatible with what we know and love. So it could be that this sort of bastard product here of a commutative thing and a non-commutative thing is really just all that we see at low energy. And at higher energies, the space-time starts to become non-commutative. And for me, that offers a possible explanation for what happens at the Planck scale. And the Planck scale is that's where it's fully non-commutative. But that's not really what my lecture is about today. That's just one of the issues and something I want to talk about. So, should space-time be non-commutative? Well, I'd like to think so. It's a very interesting avenue of research, and it opens the possibility that the standard model can actually teach us something about quantum gravity by following the successful structure in the standard model and then saying what happens when you apply that to quantum gravity. Okay, so final plug here is I was going to list loads of references, but I ran out of time. But here, if you look at my lecture notes, which is sort of an expanded version of what I've just said, and there's various references in the lecture notes. So I hope that doesn't do all the people who've contributed to this too much of an injustice to say, go away, go away and look in there. Okay, so thanks everybody.
Yeah, great. Thanks so much, John. That was beautiful. Really enjoyed listening to you and lots to think about. I myself have lots of questions, but I open it up to the audience and then maybe I can put in my questions. Kindly go ahead. Should we maybe stop? We could stop sharing the slide. Yeah. We could keep them and use the raise hand feature. Oh, yeah, good. Okay. If we need, we can share the slides. So welcome back, everybody. That was a really nice, absorbing 1 hour or a little over. If you have any questions, please go ahead. You can just use the raise hand feature and I'll unmute you. Okay, maybe I can start, John. Sure. Could we go over the status of the Lorentzian case, both for the spectral triple and what about the Kohn-Shamsuddin spectral action principle? Does it stand in the Lorentzian case?
Right. Okay, so good question. So to answer your second question first, the bit I don't know how to do is to write the spectral action for the bosonic fields in the Lorentzian framework. And I don't know how to do it for technical reasons, that I don't know enough about Lorentz. You see, in Euclidean theory, you've got the whole spectral theory of the Dirac operator on a Hilbert space, and you've got heat kernel expansions and everything. And we don't have all of that theory in the Lorentzian framework. There are some people with French names busy working on this sort of thing. So there is some theory being developed about what a spectral action in the Lorentzian framework looks like. So I think that's a developing field. And you can ask what's the analog of the heat kernel expansion in the Lorentzian framework. That's again something that's developing. So that's okay. So the fermion action, obviously, you can describe very well, and I sort of write that down. And that you can describe this in Lorentzian and Euclidean. I'm actually busy working on a project to explain how to relate the Lorentzian fermion action and the Euclidean fermion action by a process of contour rotation of the functional integral. So that's something that will hit the archive.
To add up to this, for the bosonic action, suppose as a physicist, I make an assumption. Let's assume that the Cohn-Shamsuddin spectral action principle works for the Lorentzian case and go. Would I be making a big mistake, or would it be conservative enough to work with that hypothesis?
Yeah. Just bookmark here. I think I failed to answer your first question. So you might want to come back to that, wherever it was. But to answer what you just said, the Lorentzian action has the problem that if you just try and write down the Lorentzian action for most things, typically it's badly defined in quantum field theory because of the I epsilon problem that you're trying to integrate e to the I something to infinity, and typically that doesn't work. So usually that you have some sort of I epsilon prescription, which means that you avoid the poles if you do a Fourier decomposition or something. And I think the way to understand that is it's really a rotation of a Euclidean integral to almost to a Lorentzian contour where you don't quite get there, where you get it within epsilon of a Lorentzian contour. So I think understanding this Lorentzian Euclidean rotation is sort of the key to even understanding what the definition of the Lorentzian thing is in the first place.
Okay, thank you.
Now, what was your first question?
The first part was about the spectral triple, your early slides, where you said that the Lorentzian case also can be handled, the algebra itself. So you're saying that part, the fermionic part, that part's okay, you're saying? Yeah,
fermionic part is fine. And this, the actual spectrum, if you forget the action, which as I say, I don't know, if you just look at the spectral triple, you can write down everything you need in the Lorentzian framework. The main difference is what was the Hilbert space in the Euclidean thing is now an indefinite inner product space. You have two spinors and you write, psi bar psi, integrate over space time, but that's an indefinite inner product. So you get, so it's less convenient. You can, if you want to do quantum field theory, no problem, really. That's what people do in quantum field theory all the time. But you just have to work, say, with smooth spinor fields, and that's your product, and then give up any idea of trying to complete it to a sort of Hilbert-like space. But who cares? If you're doing quantum field theory, it doesn't really matter. But as I say, I think probably a more careful description will be involving these sort of I epsilon things anyway. So it needs to be built in. But what do I want to say? Yeah. Right. So, but I think the Lorentzian framework is very important because we don't have an in principle understanding of what Euclidean physics is. I mean, there are no Euclidean physics experiments, so you can't just open a physics textbook and look up what Euclidean physics is. So what is Euclidean physics? Well, you write down Lorentzian physics and you have some process of contour rotating it to Euclidean physics, and it's whatever you find when you start with the right Lorentzian physics, as in textbooks. And so there's a very delicate relation between Lorentzian and the Euclidean theories there. That
Right.
in principle we know what the Lorentzian framework is, but mathematically it's badly defined. The Euclidean framework is mathematically better defined, but we don't actually know what the physics is. So
Yes.
it's vitally important to relate the two, and that's what I'm trying to work on at the moment.
Thank you. Thank you. I'll just read the comment that David Chester has left in the chat. It's an observation. Lorentz gauge gravity equal to the Einstein-Cartan theory has torsion, whose quantization can lead to torsional regularization to find UV complete QED. Since that result from Nikodem Poplawski is recent, Cohn and others overlooked these possibilities long ago. Gauge theory with the Lorentz group done right can actually clarify how infinity problems can be dealt with, but more work is needed. Yeah. Thank you.
Okay, yeah, so there's an interesting question, which is, you see most of the work on spectral triples, and particularly the standard model, you just say, I'm going to use the Levi-Civita connection for the spinors. And there's no torsion there. But if you're just working on a fixed space-time manifold, it doesn't really matter. The question of torsion only, I mean, you can put in torsion if you like, and then you get extra terms and so on, which would couple with the particles. Okay, fine. But torsion only becomes a big issue if you start to talk about quantum gravity, and then you're going to integrate over the space of manifold Dirac operators. In other words, over all the data in the Dirac operator itself. And then it's not really viable to say, I shall only allow Dirac operators that have the Levi-Civita connection, because then that's a nonlinear condition on the Dirac operators. And as I said in my talk, all the other conditions, or the simple ones, are all linear conditions, so they have a nice space. And when you start adding nonlinear conditions, then you get in a big mess. In any case, it's not really clear what I don't know how to write down. If you give me a Dirac operator, I don't know how to tell you whether there's torsion in it or not. I mean, I know with a connection, I can write a formalism, but if you just give me the Dirac operator, I don't know how to unscramble the connection and then tell you whether there's torsion or not. So for those reasons, when you're in a gravitational theory, you need to work with Dirac operators with torsion. So that then becomes an issue. And whoever left the comment is right, you know, that should come in. And that has not been analyzed in the context of the sort of physics context very much. There was some very good work by Christoph Stephan about Dirac operators with torsion in the spectral triple framework, in which they're described very fully, and that's very useful. But nobody's then asked, well, if I plug that back in to the gravitational spectral triple, what sort of actions do I get, and so on. That's not. Christoph did do something in those directions, but I don't think the physics of it has been investigated thoroughly. That's what I'm trying to say.
Could I ask you, John, and this in related, there has been some speculation that in the literature over the years that the weak interaction, the weak force is like gravity in many ways. And could it be that the torsion part of the geometry, the antisymmetric part of the connection, is actually related to the weak interaction? Have you come across this sort of an idea? I mean, it's like when you one thought is that when you go to Patisalam, SU to L cross SU to R, that SU to R actually could be gravity.
No, it hasn't come in as far as I know. No.
Okay, yeah, we can leave it at that. Yeah. So now then I wanted to take over the next topic that, like in this lecture series, and we saw in Cole's talk a few weeks back, we are trying to look at standard model from division algebras, including octonions and Clifford algebras point of view. where it's almost certain that the way you described it today and the way the division algebra people are trying have to be related. They're very similar structures. And do you have thoughts on that? I mean, I'll get more specific, but
I feel that with the spectral triple thing, we're plodding very slowly because we're carrying along with us all of the dynamics and all of the physics, a whole load of other stuff with us. So if in your algebraic framework you're allowed to sort of change things and have the Octonians act or something, we can't just do that. We've got to very carefully work out, well, how does that fit with everything? All the axes. And how do I? You see what I mean? So it's a very, very slow, painful process trying to change the algebra.
In the spectral triple algebra is associative, is it necessarily?
Yeah, the algebras are algebras of operators in Hilbert space, so they're associative. I mean, you can, of course, make some. There have been attempts to change that. I mean, Shane Farnsworth in particular and Latham Boyle worked on a formalism where you have a Jordan algebra and a Lie algebra, because you see you've got. So the way I described it is you have a bimodule over an algebra. So there's left action and right action. Well, you might say, well, instead of left and right, I will act with the Jordan algebra and the Lie algebra, and that's sort of somewhat similar. It's acting with anti-symmetric things and symmetric things. So they had a formalism like that, and then actually it solved some of these puzzles I had at the end. There's some of these issues in their framework get solved, but then other issues turn up. You see, so it's not cost free. But yeah, so there are some very interesting avenues, and various things have developed. So I think what I've presented is more or less what everybody agreed on back in 2006, and various other things have gone off in different directions, and one of them is this non-associative.
Okay, because one advantage one immediately sees of going over to the octonions, the algebra that you wrote down, C cross H cross M3C, very naturally unifies when you go to the octonion algebra and start working with groups like E6, for example, because that would bring together the SU2 and the SU3 in a bigger group like E6 through branching. And that's why the octonions appear very appealing. Similarly, when you write M cross F at low energies, there seems to be a way where if you go to a larger structure like the octonion algebra, instead of M cross F, you have a bigger structure, say the octonion vector space, from which if you make a quadratic form, you can have things that it starts to look like M cross F, whereas underlying it's just it's a larger space.
It could be. I mean, yeah. So there's lots of very interesting things when you make the manifold non-commutative as well as the internal space. You've then got a product space, and you can start to ask yourself, well, how do I even know which is which? How do I even know which one is space-time and which one's the internal space?
M cross F is quote unquote has the spirit of a larger space-time or a larger whatever, like Kaluza-Klein theory, but now at the not at the metric level, but at in some sense the Dirac operator level. The Dirac operator in a higher dimensional space, like instead of an quaternionic space, an octonionic space. Right.
So you can ask questions like, is the global structure even really a product, or is it something more general? Is the product structure only local, or is it only at low energy? Is it local, and so on? So there's a myriad of possibilities, but the moment, I don't
I
have a really good way of
totally
jumping
agree
on.
that in M cross F, M should also be non-commutative. And actually, I talked by Athiya once, just online. He had this very nice remark that the Dirac operator was actually discovered by Hamilton already, because he likes to think of the Dirac operator as the gradient operator on a quaternionic vector space. For the Laplacian, it's very easy to see. If I just make a gradient operator using the imaginary directions of the quaternion, its square is just minus the Laplacian. And with some more work, one can take a gradient operator on a quaternionic space, including the real direction itself, and show that the gamma matrices of the Dirac operator actually a trade-in for quaternions. I could write them using the gamma matrices using quaternions. And then the mystery of the gamma matrices disappears. It's just a quaternionic vector space. And then what one is suggesting is then let's extend that to the octonionic vector space and like write a Dirac operator for the octonionic case, which then becomes a 10D spacetime, as you know. The SL20 is the double cover of SO19. So in that language, in the language where the Dirac operator is seen as the gradient operator on a quaternionic space, essentially my underlying space is non-commutative. Spacetime is commutative, but that's a quadratic form made by squaring the quaternionic. It's like the square of the quaternionic vector space is the Minkowski line element, essentially speaking. So from that point of view, in quantum for fermions, I would like to think that space, the M is already non-commutative. That's what the Dirac operator is telling us. The Dirac operator is not just a gradient operator, it has these gamma matrices, but they are hiding in the fact that actually my space is quaternionic and hence non-commutative. I just thought this is what Athiya was trying to say. Okay. Let's see if there are more questions. Yeah, David, one more. Shamsuddin also studied torsion long ago, building off of cones, but the renormalization aspects were not fully explored. Yeah. Okay. Thank you. Thank you. Yeah. Yeah. Well, what happened to the Higgs mass prediction that went away, John? At some stage there's an excitement about.
Yeah, well, it was, yeah. So, I mean, look, everybody was very excited before the Higgs was discovered as, let's try and put a pin in the map for what our prediction of the Higgs mass. And you can make various. So the action I wrote down was the expansion of the spectral action has various constraints in it, and some of the parameters are constrained. I mean, something at the standard model has something like 18 parameters, but when you do this thing with non-commutative geometry, you only get 16. And you can ask, what does that mean, and put in some of the data you already have, and then try and predict some other things. And there was a prediction that the Higgs mass would come out to be something, and it was wrong. And it was later realized by Kahn and other people that that whole idea was flawed anyway, because the Higgs mass, the way they'd originally done it, was unstable, and that the running at the Higgs field was unstable. So the running at larger energies the quartic term would go negative, and so the whole thing wouldn't even exist.
Okay.
And the answer to that was to stabilize it, was to introduce the sigma field, which is to promote one of the constants in the Majorana mass matrix into a scalar field. And that stabilizes the Higgs mass. But when you plug that back into the spectral triple formulas, it completely changes the definition. Sorry, stabilizes the Higgs field, but it completely changes what you predict for the Higgs mass. So that original prediction, what just wasn't, with hindsight, was just a bad prediction. And actually, the way out of it is this sigma field, which the physicists sort of discovered anyway. You need to stabilize the Higgs field.
Okay, and the next comment was, you probably have know this paper from Landy and Rovelli, Dirac eigenvalues as dynamical variables for general relativity. So that is, should we say that's essentially an offshoot of the Cohn-Shamsuddin spectral action principle?
Yeah, I mean, they were trying to apply this whole idea to say, well, what can we actually measure about the gravitational field? And yeah, okay, good idea. You can measure the eigenvalues of the Dirac operator. Yeah, great, because they're invariant. They're, the diffeomorphism.
But the good thing for me there was, then I can suppose I want to quantize gravity. Then these Dirac eigenvalues are like classical observables, and quantizing, which I'll talk about in my talk 2 weeks from now, quantizing gravity would amount to raising each Dirac eigenvalue to the status of an operator. And it is useful for that operator to be the very Dirac operator of which this was an eigenvalue. So my quantum gravity dynamical observables are now infinitely many copies of the Dirac operator, which is like a momentum operator, and the conjugate configuration variable to this momentum is actually the Yang-Mills gauge field of the standard model. And that's that seems to make things interesting. So from that point of view, the Landy-Rovelli paper I thought was very valuable. It opens up a new avenue to quantizing gravity. It's much more fruitful to work with the Dirac operator, even while going to quantum gravity, than with the metric. The metric is very difficult. It is emergent. And so
the Dirac operator is much more physical. I mean, it comes directly in the standard model, whereas the metric sort of doesn't.
Right. So what we are saying is that the lesson for us from the Cohn-Shamsuddin spectral action principle is that the Einstein-Hilbert action on the whole is sort of a derived notion, and it's much better to work with the eigenvalues of the Dirac operator.
The eigenvalue, the spectrum of the Dirac operator is a bit tricky because it's an unordered set. So when you say, so it's very hard to talk about an eigenvalue because, which one? And
all of them, the infinite.
Well, yeah, you can talk about the set of all of them at once.
That's what's
talk about
intended.
the 10th eigenvalue is very hard because because as you change the Dirac operator, the 10th and 11th might come together and then they come apart again. And then, well, which one was which?
Okay, so when I say let's quantize all the eigenvalues, you're saying there's a counting problem.
Well, what we do, I mean, much cleaner is to quantize the space of Dirac operators, and we do that. We because the Dirac operators is a linear space. As I said, all the constraints are linear. If you forget the infinite dimensional business, if you just work on finite dimensional spaces, which is what we do, the Dirac operators is a linear space, and you can just integrate over it. It's just ordinary integration. So you can do quantum gravity by integrating over the Dirac operators. Now, like any matrix model, you can rewrite that if you're lucky in terms of some sort of integral over the eigenvalues and with some sort of measure. And
that gets us very close to Steve Adler talked about his matrix models.
But the eigenvalue picture is complicated. I mean, for a simple matrix model, a single random one matrix model, you can change variables from the matrix to the eigenvalues with some measure factors. But when you start, so you can think of Dirac operators, non-commutative Dirac operators, ensembles of them, as random matrix models for a number of matrices. You could, when you have that formula for the Dirac operator, there's a sum of terms. There's a sum of various matrices coming in, and they're now random. So you end up with a multi-matrix model. But turning that into an integral over eigenvalues would be very, very hard and very messy and might not even...
No, I actually intend to work with the Dirac operator.
Okay, great. Yeah.
But with some sort of understanding that I arrived at the Dirac operator by quantizing its eigenvalues, and hence had a infinite copy of Dirac. I started with one Dirac operator. I had its eigenvalues on the manifold. I quantized each one of them so that it again became a Dirac operator. And then I have a infinite family of Dirac operators, which together are supposed to describe all the degrees of freedom of a quantum field. So probably my last question is, have you come across the Tomita-Takesaki theorem, which Kohns is very fond of? He talks of there being a new time parameter, which is unique to non-commutative geometry. It'll be great to hear your thoughts on that.
Well, this modular operator, I mean, that's where the J comes from, the real structure. I mean, when you have von Neumann algebras, you have an algebra, and then you have its commutant, and the Hilbert space is then a bimodule with the left action of the algebra and the right action of the commutant. And in this Tomita theory, J is the involution that switches from one to the other. So that's probably where the idea of the real structure actually came from in the first place. Okay.
So would it be a valid thing to say that along with the space-time, 4D space-time manifold, in this 4D space-time manifold, my time coordinate t is not really the time that flows. It could have been Euclidean for all I care. X, Y, Z, t, all Euclidean. This is evolving in what we call the Tomita-Takesaki Kohns time, or related to your real structure. Would you be okay with that kind of a claim? The space-time manifold evolves in the Tomita-Takesaki time.
I don't know. I'm very much a space-time person, and I don't tend to think of time as evolving linearly. So
what is the Tomita-Takesaki time doing then? I mean, is it fundamental? Is it a part of nature? Because nature is fundamentally as a non-commutative geometry.
Good question. It could be that it's something like when you have a thermodynamic ensemble, you have time and imaginary time. So it's probably something to do with that. But you're getting me out of things I really understand.
Yeah, because one thing which struck me is that when you say the spectral action principle, you actually start with the Einstein-Hilbert action with the space-time volume integral. The left-hand side, which you call the spectral action, has lost the... if I want to use it as an action, it should have a time integral. So,
no, it's very much a space-time picture. You just have a Dirac operator on the whole of space-time, and you take the trace of some function of the Dirac operator.
Right.
I could say a lot more about what that function is. I mean, the Kohn-Chamstein thing is a cutoff function, which is inherently unphysical, in the sense that it tends to lead you to a cosmological constant. And
well, one thing which worries me, if I may put it that way, some of these problems are problems from a mathematician's point of view, which physicists tend to gloss over. And for them, it's, yeah, I mean, it's okay. There is a cutoff function. I assume that it exists, and it's, let's say, doesn't bother me as a physicist. For me, trace d square is the Einstein-Hilbert action, plus some corrections. But I don't worry so much about f or chi.
Well, no, I mean, from my perspective, that the whole idea of the cutoff function isn't really something that's going to work, and that because it ignores an infinite number of eigenvalues above the cutoff, but the whole thing is just a problem from starting with the idea that the Dirac should have an infinite spectrum to start with is where the problem sets in. So if you go to non-commutative spacetimes, you can now perfectly well have a finite spectrum of the Dirac operator. So
I mean, if the universe is a closed universe, if the universe is a closed universe, would life be easier from this point of view?
Yeah, possibly. Yeah, because but yeah. So the thing is, so there's two things. So what I'm trying to say is that the idea of an infinite spectrum that goes all the way up to infinity that needs cutting off is problematic. You could still have an infinite spectrum, but you could still have an infinite number of infinite dimensional Hilbert space, an infinite number of eigenvalues, but still only have a finite range. And then you wouldn't need a cutoff, or you could even have just a finite number of them, and you definitely don't need a cutoff. So I think either of those two is preferable to having an infinite spectrum of the Dirac operator. But it's all a question of what the structure at the Planck scale is, and nobody's going to tell you that from looking at the standard model. I mean, some other physics is coming in, some gravitational.
So if my space-time is also non-commutative, that is helpful in some sense.
Very much so, yeah. Very much.
Yeah, so one more comment from David Chester, I'll read it out. A massive particle leads to a Cartan radius where the torsion deforms the Heisenberg algebra and leads to momentum quantization and changes the spectrum. The Cartan radius is larger than the Planck scale for the electron. Yes, true.
Okay, thank you.
More questions, please. Roger, just want to say good evening to you.
Hello, Roger.
If you like, you could kindly
unmute. Muted, Roger, if you want to demute. You just want to say hello. You're muted.
You could kindly try to unmute yourself if possible.
Hello, I'm unmuted now, I think.
Yes, you are.
Yes.
No, I just wanted to apologize. I was very late joining for some technical reason. But
sorry about
that. Any thoughts, Roger, on Cohn's non-commutative geometry?
Well, I suppose I could make a historical comment, which is of some interest. I mean, I think when Dirac, somebody was looking through Dirac's old papers and found in his old papers, there was little pictures of Pappus's theorem as though it was false. And the reason he'd been studying this, I think Heisenberg had been giving talks on quantum mechanics. And this is in the very, very early stages. You see, Dirac had not even come into the picture. But Heisenberg had been giving talks about non-commutative operators. And Dirac, who at that time used to attend meetings that H.F. Baker had, and he talked about non-commutative geometries. And the idea was that the characteristic of a geometry which is non-commutative is that Pappus's theorem is not true. And so you could see in Dirac's very old papers, I mean, this just his notes, what he was, when he was getting interested in quantum mechanics, he was drawing Pappus's theorem as though it was not true. So clearly he was exploring the idea that you could have in ordinary geometry at a sort of small scale, I suppose the idea was that the ordinary space-time geometry might in some sense be a non-commutative geometry, which is very curious because he'd never confessed to being studying this. And this was his early interest in projective geometry, that you could have these non-commutative projective geometries. I don't know what influence that he had on what he did later, but it is quite interesting as a historical comment that he was exploring these ideas at that time.
Yeah, thank you, Roger. So this would be in the light of general relativity having already been around for a few years.
Yes, well, general relativity had been around, yes.
Yes.
I guess let's see, I'm trying to think of the yes, but quantum mechanics, I suppose, had not been developed very far. And so he was thinking of the space-time being in some sense a non-commutative geometry. I suppose it led him to his way of thinking about quantum operators and things like this, but
Yeah,
it did.
probably the genesis of the Dirac operator might even have something to do. Although I don't know whether he knew about quaternions at that stage.
I don't know what he knew, I'm afraid. I have no idea.
Yeah, Bernd, please go ahead. Please go ahead.
This would be of interest for me because I know that projective geometries over the quaternions do not satisfy Pappus' law because the quaternions are not non-commutative. Yes. These were one of the first examples where people knew the failure of Pappus' theorem. So,
yes, the failure of Pappus' theorem is the condition for
non-commutative. Exactly. Yes. And this was first discovered by looking at projective geometries over the quaternions, which were also the first.
Oh, I see. Yes, sure. That would be an example. Yes.
And did Dirac, in his early writings, wrote something about this?
Sorry, what?
Did Dirac write something about this in his earlier writings?
Me?
No, Dirac.
Did Dirac publish this?
I don't think. You see, Dirac was very secretive about where his ideas came from.
Okay.
He didn't want to talk about things which he might think were not correct, you see. And I suppose where he was led after this was not along those particular lines. I mean, he didn't think of space-time geometry as being non-commutative. And so maybe he thought it was a mistake to think along those lines and therefore didn't want to write about it. I have no idea.
Yeah, we were just talking to, sorry, but I'll come back. We're just talking to John just now. Yeah. The Dirac operator, if thought in the language of a quaternionic vector space, I can rewrite the gamma matrices using Pauli matrices and go to quaternions already at the level of the Dirac operator.
Which possibly did influence him, yes. I mean, it could be, yeah. I don't know.
It has already become non-commutative.
Yes.
The Dirac operator is a reflection of non-commutativity at the space-time level.
Well, that's the question. Was it relevant at the space-time level? And I don't know. I mean, because of course, the Dirac electron doesn't have anything to do with the space-time being non-commutative. So he may they may have thought of that as being a wrong direction. I don't know. See, it's very hard to.
How would you say, Roger, why are there gamma matrices in the Dirac operator? Why do we need them? I mean, I was thinking we need them because quaternions are already playing a role there.
Well, it's a different signal. I mean, they're clearly related to quaternions, but the quaternions are positive definite space, four-dimensional space or something. So it's not really space-time.
Yeah, so we have to wiggle it around, something like split quaternions or split biquaternions. We get there, but it's not straightforward, like you correctly said, because the quaternions would give us a positive definite quadratic form. So if you want a Minkowski line element from there, we have to
do some. You don't really need to put in the gamma matrices or anything. I mean,
David wrote something in the chat, maybe.
Okay. David, David, would you like to? If your audio good? But Bernd, could you read these out, Bernd, please, and then we go to your comments.
David cannot unmute. He writes that he's not able to
Okay,
unmute.
I tried to unmute him. Sometimes the audio doesn't go well. Yeah, yeah. Go ahead, David.
Hey, yeah, so overall, I've just noticed that a lot of people talk about geometry that is non-commutative, and then there's this term of non-commutative geometry. And so I just had a question whether when we talk about non-commutative geometric structures, is that necessarily have to be Cohn's notion of non-commutative
No,
geometry, or
there's all
are
sorts
there
of
other types?
Yeah, I mean, when people say non-commutative geometry, there's a variety of different things that people mean by that. And so it's not, and usually it's somewhere or other there's an algebra that becomes non-commutative. That's sort of common. You know, the algebra of functions, instead of being commutative, its replacement is now non-commutative. But that's not really enough to give you a geometry. You need more structure to give you a geometry. And then you can choose various things to try and generalize to make it a non-commutative geometry. And different people pick on different things and say, aha, this is my favorite non-commutative geometry. For example, there's a big industry in having the algebra of differential forms over a non-commutative algebra. And then saying, well, that is somehow non-commutative geometry. And there's various other things you can turn into. You know, there's the fuzzy spaces of John Madore, for example, and Jens Hopper, where they wrote down matrix algebra and then a Laplace operator on a matrix algebra. Non-commutative geometry. Okay, fine. You know, you can do stuff with it. So there's lots of different flavors of non-commutative geometry that are not spectral triples. And usually they're less specific. There's less structure to them in the mathematical sense than in spectral triples. So you can do some of the same things, but then you sort of get stuck somewhere because they're too general and allow lots of stuff that is sort of arbitrary. So another approach, you can just pick, you can have a non-commutative algebra and pick a set of generators and call them the non-commutative coordinates for a space. And then you can make some progress. But at some point you get stuck because your scheme isn't really specific or isn't really constrained enough, doesn't really have enough axioms and properties to really give you a lot of geometric theory. So when I say non-commutative geometry, I mean spectral triples, because to my mind, that's the most complete theory of non-commutative geometry there is. It's non-commutative Riemannian geometry, whereas a lot of other non-commutative geometry is just non-commutative some other sort of geometry, which is fine, but it's not what I'm interested in. I mean, for example, quantum mechanics is non-commutative symplectic geometry somehow. So, you know, discuss, but it's not enough to talk about spectral triples. So, but for me, you know, the spectral triples is the important thing because A, I'm interested in Riemannian geometry as a quantum gravity person, and B, because the standard model seems to be full of all that structure. So, absolutely. Yeah. So when I say non-commutative geometry, that's what I mean.
It just looks like non-Riemannian geometry might be necessary for quantum gravity. It's kind of like the smallest forms of gravitation are torsion and non-metricity. So if we want to study quantum gravity, we might want to first include the smallest forms of classical gravitation and at least be open-minded.
Well, torsion goes in the spectral triple thing very, very well. I mean, that, in fact, you know, really, if you're going to discuss gravity in spectral triples, you're going to have torsion in there. So that's fine. Non-metricity, no, not so much, because the whole point of the spectral triple is you can recover a metric from it. So no, that's probably not going to come out. But,
well, non-metricity describes zero-dimensional defects, so it might help with some things when things break down at singularities. Who knows? Yeah. Thanks. Yeah, I appreciate all those comments. It's interesting. Yeah. But yeah, just in terms of what other people are talking about with like non-commutative structure of space-time, I just think it's very natural to just think of operators of position and momentum, and just to point out that essentially the structure constants, except the constants would now be functions over space-time. Those refer to torsion of space-time and energy momentum. So if you had torsion of energy momentum, that would literally relate to non-commutativity of space-time. but it's pretty exotic differential geometry that hasn't been fully developed yet.
Yeah, I mean, there's a sort of a mantra which occasionally I think I understand and then realize I don't, which is that curvature in position space is non-commutative to momentum space and vice versa.
Ah, Born duality. It's called Born duality. It was developed, I think, in the 1930s and 1940s by Max by Born, who noticed that a curved momentum space corresponds to a curved position space and vice versa. And
yeah, right. Thank you. Yes. So, I mean, I sort of understand this, and occasionally I can do some examples where it happens, but whenever I try and write it down in general, it sort of disintegrates as a general principle.
So, Roger, I just wanted to make a short remark on how to get a Minkowski line element from an underlying sometimes the form, like if I take the square modulus of a complex number x plus iy, then I get a positive definite form x squared plus y squared. But instead, if I look at the split complex number x plus omega y, where omega square is 1, but omega is neither 1 or minus 1, the modulus square is an x square minus y square. So somehow, if we give more importance to the split complex numbers, we can get, I think, Lorentzian quadratic forms out.
Well, I don't know. I'm not sure I like the idea of split complex numbers. They look to me just like a pair of real numbers.
Okay, yes, yes.
The beauty of complex analysis is dependent upon them being not split. And so if they're split,
okay.
you lose the whole beauty of the theory, as far as I'm concerned.
Okay. That's very interesting. That's very so okay. So when you had the split octonions, you are saying still retain this quality of complexity.
Yeah.
Is that true?
Split octonions.
Yeah.
I was never terribly keen on them either. You see, split octonians. Sorry, I thought you said quaternions. A split octonions.
Yes.
Well, they fit in naturally with the Lorentzian signature of space-time. So that's where that comes from. No,
okay.
And you see, you get these split signature. I mean, the Lorentzian signature of space-time is associated with the conformal group, which is O24.
Okay.
And then the spinor version, or the twistor version of that, is a quadratic form, which is 4 pluses and 4 minuses. Okay,
so you are saying a split octonion is a more natural structure than a split complex number?
Yes.
Okay, thank you.
If I can come in, I took that to be exactly the message of the talk that you gave, Roger, at the beginning of this series.
Yeah, that's very interesting. I was naively putting split complex numbers and split octonions.
No.
The
These
same footing.
Honest complex numbers, very much so. And then the twistor space is a complex space. Yes. But then you see the quadratic form when you take complex conjugates. You have a split form which is 4 pluses and 4 minuses. And the split octonions come out naturally with respect to that.
So this is two 4-dimensional space-times? If I have 4 plus 4 minuses?
No. Okay. No, it's just that these numbers are not. I mean, the twistor space is a complex 4-dimensional space, but you have a quadratic form, which is a Hermitian form, but that's a pseudo Hermitian form, which has 4 pluses and 4 minuses.
Yeah.
Yes, I agree. I understand.
By the way, I mean, to bring that back to non-commutative geometry, it seems to me the one axiom you can really ditch but still carry on working with is the axiom that the Hilbert space is positive definite. So, for example, if you have a a chirality operator which has positive and negative eigenvalues. You can stick that in the inner product and make a new inner product, and that's now indefinite. And it has a load of positive eigenvalues and a load of positive, it's indefinite, a load of positive directions, a load of negative directions. And none of the other axioms are really sort of upset by doing that. It becomes unfamiliar and a bit more tricky to work with, but nothing sort of goes wrong. So that fits very nicely with this whole idea of looking at these split structures.
Mm-hmm.
And it does also fit in with the Lorentzian framework. I mean, there's a bit, for example, this is what I was trying to say. You might wonder if the internal space of the standard model could have an indefinite inner product. And there are versions of it where you reverse the sign on some of the directions, and you get some slightly different physics and so on.
Mm-hmm.
So I think it is an interesting direction.
But you were saying something. Sorry, I interrupted you. You have something more to say? Yeah.
I just wanted to say thank you to David because he provided some references, but I would have a question going back to curved momentum space, because he wrote something in the chat. What would non-metricity in energy momentum space mean?
Well, so if you had, you can get torsion as the commutator of P and P, but that's space-time torsion connected to the momentum operator. So the dual reciprocal Born reciprocal relation would say that commutators of space-time with space-time operators give torsion of energy momentum space.
People still here? Oh, good. Yeah.
So that hasn't really been studied in much detail yet. There was some non-commutative space-time work. If you look at like work of Snyder going back to 1947, there's a bunch of work where they'll try to get non-commutative structures, but it's like they'll have constants on the right-hand side. But the point is to realize that the right-hand side of these commutation relations for operators are functions, or they're fields, they're gravitational fields. So it's like the structure constants depend on space-time, they depend on position. And so you can get a more dynamical, you can get the spectra to be dynamical within themselves, but no one's gone there yet. So, I mean, gravity might say that, let's just not worry about matter and then discretize things. And then it's like, well, how is it exactly discretized? It's like, well, it kind of depends on the matter content that you're ignoring. So, yeah, we're getting there. It'll take a lot more work.
Okay, thank you. I was just curious.
One thing I forgot to ask is, John, the Cohn-Chomsky spectral action principle, is it very specific to the standard model gauge structure, or would it work if my gauge fields were including SU2R like Pati-Salam?
Yeah, no, you can still write a spectral action. That's right. No, that bit of the theory works fine.
Okay. And one thing I always found fascinating about the spectral action principle, it gives conformal gravity, which we sort of, in the wild square, which we sort of don't know what to do with. What is its significance for nature? If we take the spectral action principle at face value, it's telling us that general relativity is not the whole story.
Well, you get that as one of the higher curvature terms, but you don't get it on its own. I mean, I don't think you could get rid of the Einstein-Hilbert term. So it's Einstein-Hilbert plus Weyl squared.
No, I agree. Plus, but it is as if suggesting that in some domain, GR is modified by a conformally invariant.
Yeah. Right. So I don't know. I'm not enough of a cosmologist to know what that really means.
For example, Mond, Milgram's Mond has that kind of a character. It's a scale invariant on cosmic scales. And if you take the spectral action principle seriously, it's in some way suggesting MOND. I mean, that's how I'm tempted to think that it's there already in the spectral action principle that.
Well, yeah. I mean, it certainly can't be true that the Einstein-Hilbert action is fundamental, because, you know, when you look at runnings of couplings, it's clear that you'll get other curvature terms coming in at different energy. You know, if you get rid of them at one energy scale, they'll come in at other energy scales. And so it's completely unrealistic to chase them away for good everywhere. So when we tend to think of the theory as being simple on the high energy scale, so at the low energy scale you get something very complicated. So you almost end up with higher curvature terms.
Sorry to interrupt you. That the wild square term is coming at the same order as the Young-Mills term. So that is very striking, isn't it? Because Young-Mills terms are playing a role in nature. They're there for the standard model. So it was
but that's because there isn't a lower order term to mask them, whereas in the gravity case, the Einstein-Hilbert term is so much larger.
Yes, but what could be happening is that, like what Milgram says, if the acceleration scale is higher than some critical scale, then general Einstein-Hilbert dominates. But for lower accelerations, MOND dominates. So something like that could be not necessarily going to the early universe, but even in our universe.
At some low energy scale?
Not energy. For Milgram's MOND, it is the acceleration, the 3 acceleration of gravitating objects. So what is like, what's seen in galaxy rotation curves is that when the acceleration of orbiting star falls below some critical universal value A0, the velocities are no longer Keplerian.
I know what you mean. Yes. Right. Well, it's possible. I mean, I don't claim to be a cosmologist or an astrophysicist, so that I'll leave that up to them.
I mean, maybe we could ask Roger. I'm sure he's thought a lot about it. Would you modify general relativity at the classical level at large cosmic distances, or?
Well, you see, in conformal cyclic cosmology, you have the large and the small coming together. So you have to have a conformally invariant scheme in order to match the two. And there's some interesting ideas there. But I'm going to have to leave. So
great.
Thank you very much for the talk. It's very interesting. I wish I understood more of it and how it fits in with perhaps the split octonions, which interest me particularly. But it looked like very interesting ideas.
I did work out some of the algebra related to your twistor stuff with the non-commutative things. And the split signature did come in there, I seem to remember. To dig up my old notes, but it'd be interesting to talk about that more some other time.
Yes, it would be interesting to follow that up more. I'm certainly intrigued by how you managed to fit in all the actual physics that we know about. I mean, the groups that are seen to be part of physics. I think that's really good. Yeah. Okay, I have to say goodbye for the moment.
Very nice to have had you, Roger.
Good. No, very nice to be here. Bye for now.
Bye for now. Bye. Yeah. Michael, we should also wind up. I guess we're getting to 2.5 hours.
Yes, unfortunately, I think we're now coming very close to the point where our Zoom window actually cuts out, because there is a limit. I think it's at 2.5 hours for the actual total length of the call. Do you want to say, or perhaps even more to the point, does John want to say a few words in summary before we close?
Yeah, well, what can I say? I think there's lots of ideas around about algebraic structure, and particularly in the standard model, which I think are very interesting, and I would like to sort of somehow filter them through the lens of non-commutative geometry and say, well, which ones stand up
So-
here, because it gives you a window into all the rest of physics and the dynamics and the action principle and so on.
Can I make one very super quick remark in connection with that? Because it's actually comes to my mind because of what David has written here in the chat about Smolin's remark that a quantum gravity regime could involve non-Riemannian geometry over phase space, which would lead to independent notions of curvature, torsion, non-metricity, and over space-time and over energy momentum space, respectively. But of course, the idea that the non-commutativity might show up naturally at the level of the algebraic structures over phase space is one of the key ideas that Basil Hiley and his co-workers have been pursuing, and particularly the role of the left and right ideals in the algebra in controlling this kind of non-commutativity over phase space. And I think that it'd be very interesting to see if there's any possible connection there with what I agree is the more mathematically detailed and perhaps clearly motivated spectral triples construction coming out of Cohn's vision of non-commutative geometry. The one worry I've always had about Cohn's version of non-geometry and some non-commutativity, non-commutative geometries, is that I still don't understand what the general notion of a mapping between spaces in the non-commutative setting is for Cohn. I mean, he seems to want to build. He seems to want to build the definition over the bimodules, but I'm not sure that gives him a general enough notion of a mapping between spaces in that setting.
Good question.
Yeah. But I'm sorry, I shouldn't really have used up. I just want to ask if you had any further remarks to make, or to Jinder.
Yeah, John, could I ask you, what do you have an idea why this doesn't excite particle physicists or phenomenologists? The algebraic approach to the standard model, like you described today, or with division algebras. I think there's something fundamental going on here, which tells us why the standard model is what it is. Other than the algebraic way, would have probably never learned this.
Yeah, I think the truth of it is that most physicists don't understand this stuff, and that's partly why I'm giving this lecture, because I want to sort of make it more understandable and more widely known, and perhaps it might enter the mainstream a bit more.
If we, for example, in the algebraic approach, started deriving fundamental dimensionless constants like the Higgs mass was attempted, do you think that would get them more excited, or they would still not care? What is it that they would like from us to get them, charged up that this is important?
Well, I think it'd have to be some big prediction that they hadn't thought of that would come up.
Like, for example, you have right-handed neutrinos, but you are saying that's not big enough.
Well, yeah, maybe if we get the structure of the neutrino sector right, and they're going to measure that in the next few years, maybe that would get some attention. But I bet there's a number of other people who, I mean, every possible neutrino paper under the sun has probably already been written. So there's probably a load of other people who can claim that they got it right. But yeah, I don't know, perhaps
if we could derive neutrino mixing parameters from the algebra.
Perhaps if we really got the unification story right, and then that predicted some low energy consequences, which you couldn't get at some other way, that would be a
Unification includes gravity, you're saying?
Doesn't have to, but even just a high energy physics unification. Yeah, I'm not sure we've really got that straight yet, but there's some ideas. And
there, John, I want to sort of make one remark that, like the Dirac equation, which in a sense is involving quaternions, is not at high energies. It is at everyday energies. Now, suppose we extend it from quaternions to octonions, we already start seeing much more structure. If I write the Dirac equation, let's say on octonionic space, or using gamma matrices for 10 space-time dimensions. So long as I can account for where those extra dimensions are, I'm not really going to high energies. I'm just working with the non-commutative space.
Yeah, but Clifford algebras aren't really a big deal. I mean, you just end up with some operators acting on tangent space in
Right.
spinors or something, and then you pick a basis and you get gamma matrices. It's not.
I agree. But when we go to octonions, we start to see.
Yeah, I don't know. It's different. I mean, because they're slightly non-associative, then obviously that's a different framework.
We start seeing more information about the standard model than if we see just using the normal Dirac 4D.
I don't know. I mean, the bit where I always stop is that if you have octonions, you have G2 as the symmetry group, and nobody ever explains to me how G2 breaks to SU3. It's just, oh, there is some choice, but why? Is there either Higgs field, or what's the physical mechanism?
No, but at least suppose I start, let's say, with E8 or E8 cross E8, and I can, even assuming a branching which gives me SU3 and electroweak, if I can explain what we see, I would say at least I have one breaking pattern which explains what we are seeing in the universe.
Yeah, but I want to know what does the breaking. I want to know where's the Higgs field.
Okay. For me, that's why the breaking does not necessarily involve high energy physics. It is the quantum to classical transition itself.
Yeah, but then you need to explain that.
Okay, maybe I talk a little bit the next time. My talk is after.
We're getting off at a tangent here, but I think all these higher algebraic structures are very interesting, but then you have to really provide an explanation as to how it descends to the low energy structure we see. Yeah.
So what I was contesting was a high energy, low energy picture. I mean, to my mind, we already have some bit of non-commutativity even at low energies, and that's what the Dirac operator, to my mind, does actually. We cannot solve the electron with the Klein-Gordon equation. We need the Dirac equation because fermions need that bit of non-commutativity even at low energies. Yeah, I know the particle physics.
Feels like time to wrap up.
Sorry, yes, right, yes.
I think that probably is a good note on which to wrap up, because I think we're going to lose our connection almost any moment. Can I just refer people to the chat if they haven't already? David has got some very interesting postings in the chat together with various responses to them that would justify an entire seminar on their own, which indeed. David, you are actually talking at some later point, aren't you, in the series?
Yes. Yeah, right at the end of September, I'll talk about
yes,
E8.
okay. Well, I'm looking forward to that very much. But in the meantime, can we all say a very big thank you to John for an immensely rich and deep-going and far-ranging talk. Dare I say, I think that talk and all of the talks have really justified our decision to launch this group. I'm very excited with the way it's going.
With your recordings, Michael, you are collecting a treasure.
Yes, so I say it myself. I think we are. But this particular series is going to be very much one of the crown jewels within that treasure, I think. Anyway, all of the talks in this series are now up on the OSMU 2023 YouTube site, and this one will be up within the next few days. I've actually already spoken to Adrian about the problem. The two talks which were the interlopers were put up by somebody else who had misunderstood our instructions as to which site he was supposed to put those talks up on. So we'll get that sorted out. Okay. Can you just thanks once again to everybody, and especially to John, for a wonderful, wonderful seminar.